All right, this is Unit 10, Lesson 3, and our topic today is called cross sections. So if you imagine sort of this water holding container that's in the shape of a cylinder, if you imagine sort of the water flowing out the bottom of this container, at first it's full right to the top, like the water container on the left side. And as the water pours out, that water level just sort of gets lower and lower and lower and lower until the container is empty. So if we think about the surface of the water as that water tank or water container slowly empties out, the surface of the water stays exactly the same the whole time. When it's full, that surface is a circle, and as it empties out, it's still a circle. It's just a circle that's lower, but that surface itself, the surface of the water, is just a circle. So I want you to imagine the water pouring from that upper container into this lower container. Now it is also a cylinder, but it is a cylinder that is tipped over on its side like shown in the picture. So I want you to think about, as the water poured into that cylinder, what would the surface of the water look like? So here's what it would look like. So at first, when the water level is low, the surface of the water would be a rectangle, and you can kind of see in the image where that rectangle is laying flat, right there. And as the water level rises, that rectangle is going to have the same length each time, which is the length of the cylinder, but the width of the rectangle is going to get a little bit wider than it was originally. And then when it reaches sort of that middle, it's going to be a rectangle that has a width that's the same as the diameter of the circle, or sorry, the diameter of the cylinder. And then this would be what we normally call the height of the cylinder, but this one's tipped over. And then after that point, after that halfway point, as it fills up higher and higher into the cylinder, that width starts decreasing. And when it gets, filled up to the top, the surface of the water would just be, basically a really thin line. So in class we did a little task, but obviously for the video you won't be doing that. So cross sections are two-dimensional shapes that are formed when a three-dimensional object is sliced. A lot like thinking about the surface of water in a container. So we've got an object here. We have a nice little rectangular prism right over here. This plane is intersecting that rectangular prism like shown in the second image, and if you were able to break it apart and sort of focus just on what that surface would look like, that surface is the cross section. So in this case, my cross section would be a little rectangle just like that. So in other words, today what we're trying to do is to look at three-dimensional objects and sort of figure out what their two-dimensional slices would be. So here's a couple of examples. We've got a cylinder on the top row there. So if we slice that cylinder horizontally and we sort of break it open and look at that cross section would be a circle. That second one down is a triangular prism. If I slice it vertically, straight up and down, and sort of break it open and look at it, my cross section would be a triangle, and a rectangular prism like shown that we saw already. If I slice that object and look at that cross section, it would be a rectangle. Now again, this shape is not a cross section, and this shape is not a cross section. This chunk is not a cross section. Cross sections are not chunks. Cross sections are like two-dimensional shapes. They're just two-dimensional surfaces. They'll have a length, they'll have a width, but they are not chunks. They are flat. So this is showing you a cone being sliced in different ways. So a lot of objects, if we find cross sections of them, the cross section will be different depending on how we slice that object. So if you think about a cone, if I slice it vertically perpendicular to its base, so in an up and down direction, that's going to give me a triangular cross section. So it'll just be this flat triangle shaped cross section. But if I slice that same cone parallel to the base, so like in the same direction as the base, in this case that would be horizontal, if I looked at the cross section there, it would be a circle. If I sliced it diagonally through the base, parallel to this side over here, it's actually going to create a parabolic shape. Kind of like half of an oval, but it's actually truly a parabola. Like we could write the equation of it using quadratics. So it's a sort of a 1-3-5 relationship right there. And then finally, if you slice it diagonally, but not through the base, it'll create an ellipse. So it's just, you know, if you sliced it exactly flat, parallel to the base, it'll be a perfect circle. If you tilt it up a little bit, it's going to just elongate that circle into an ellipse. If a slice is parallel to the base of a shape like a pyramid or a prism or a cone, then that two-dimensional cross-section is going to be similar to the base. So for example, if you have a cone that has a nice circular base, if you slice it parallel, you're going to get a circle. If you slice it at an angle, you're going to get an ellipse. And below here we have a pyramid. If you slice that pyramid parallel to the base, maybe you know that this is a square pyramid. If you slice it parallel, you're going to get another square. But if you tilt it a little bit, it's going to change that shape. I'll try to draw it. So if I tilted it a little bit at an angle and sliced here, I would end up, whoops, there we go. And it's hard to see with actually a trapezoid because this upper edge is going to be a little bit shorter than this lower edge. So this would be kind of matching up like that. So parallel would be the same shape. If it's exactly a flat slice, it'll be the same shape, a similar shape to the base. But if you angle it a little bit, it'll change. The maximum number of edges that the two-dimensional cross-section can have is going to be equal to the number of faces of the three-dimensional figure. So a cube, like a dice, has 6 faces. So if I plan my cut correctly, I can manage to get up to a hexagon. So this image is a little tricky to see, but there's if you slice at the right angle, you can get a hexagon. You would start sort of diagonally on the top face and angle your knife down and back, coming out the lower base, and you would manage to hit those other 2 sides as you did, creating a hexagon. So I could also cut a cube to get a pentagon. I would just angle it a little bit less so that my knife didn't come out the bottom. And of course I could get a 4-sided shape. I could get a triangle. But the most sides the cross section could have is 6. So for example, if I have an octagonal prism, so that means that it has 8 edges for the base. So the base of this has 1, 2, 3, 4, 5, 6, 7, 8. If I cut it correctly, because it also has a top and bottom, I could get up to a 10-sided object, or a 10-sided cross section. So here's a hexagonal prism. That just means its base is a hexagon. I want to kind of think about what my cross sections would look like. First of all, if I sliced it horizontally parallel to the base, so if I sliced it like this, my cross section would end up being similar to the base, so my cross section would be a hexagon. If I slice it vertically, I'm going to end up getting, and I'll try to draw it, if I sliced it vertically, maybe you can see that that would be a rectangle. If I sliced it vertically, like more towards the edge, I would still get a rectangle, but I would just get a smaller one. Is it possible to slice this so that I get an octagon? Well, it is, because we have 6 lateral faces. So 6 of these that go up and down, they're called lateral faces. Plus, we have the top and the bottom. So because of that, we have 8 total faces, which means if you angled your knife at the right direction, you could get an octagon. You could get an 8-sided cross section. Let me show you kind of a visual. Oops, broke my smartboard. Let me see if I can pull up a visual of this for you. Hold on just a second. So this will show you maybe some of the possible cross sections. Right now it's showing a double cone, so I'm going to switch it to a single cone. So I can adjust that cross section to be at different angles, and what it's displaying over here is the shape of the cross section, and then this is showing you sort of 3-dimensionally what it looks like. So I can move it around so you can see different sides of that, or from different angles. So if I move that slice up higher on the cone, the cross section is getting smaller. If I move it down towards the base, it's getting larger. And if I take it off to different angles, let's see, it's going to kind of elongate it. Let's see if I can move that. You can kind of see the parabola there. And if I kind of go in the other direction, you can kind of start to see it become an ellipse. I need to move it up a little. There we go. There's a nice ellipse. So just depending on the angle, and you can see I'm just slicing it sort of at a pretty steep angle there. Kind of fun to play with. So here's a prism. This one has, here's a cube. Okay, so this is like a dice, a nice little block. So right now it's more or less, change it a little bit. Oops. Right there is more or less a rectangle. If I angle it a little bit, you can see that there's the hexagon. It's not a perfectly regular hexagon, but it has 6 sides, and I can change it. So here it's kind of more of a diamond parallelogram shape, and it just depends where I cut it and which angle it gets cut at. So lots of different shapes possible when you're doing cross sections, and you just have to kind of, there's a nice pentagon. So it's just slicing off, you know, that far side, and it's creating that nice diamond, like almost Superman shape. So anyway, if you have a hard time visualizing these, sometimes playing with some of these online things can help. So if I had a block like this and I wanted to get a triangular cross section, I could just slice off one of the corners, like if I slice here and sort of down and angle out, it's going to create a nice triangle. You can get a rectangle several ways, but one way would just be to cut like this. To get a square, you could just slice it horizontally or vertically. To get a parallelogram, if you slice at an angle, it'll sort of elongate it into a parallelogram shape. I'm not going to try, oh, a trapezoid. I'll show you trapezoid. Then I'm not going to try to draw the hexagon. So to get a trapezoid, if you kind of start near to one of the vertices of the cube, and if you angle down towards the base as you cut, you'll get a nice trapezoid shape. A cube has 6 sides or 6 faces. So could we get a pentagon which has 5 sides. We definitely could. Oh, not yet. Yes, good grief. Could we get a circle? Is there any way to cut this thing, in a straight slice to get a circle? And that would definitely be no. An octagon would also not be possible. And I definitely can get a triangle, but it would actually be impossible to get an obtuse triangle because there are no angles in this shape greater than 90 degrees. So no matter how I cut it, I'm going to end up, it's not going to work out to get an obtuse triangle. All right, so from a cylinder, if I'm thinking about it horizontally, I'll get a circle. Vertically, I'm going to get a rectangle. If I cut it at an angle, I'm going to get sort of an oval shape. If we cut it sort of through the base, we'll get sort of a half oval. Ooh, I'm not drawing that very well. Sorry. Let's see. There we go. That's a little better. Doesn't really have a specific name. This one's actually not a true parabola. All right, so we're just going to use cross sections to help us with a couple of calculations now. So this says a planar cross section of a right circular cylinder is shown. We want to know what is the area of the cross section, and it gives us 4 choices. Now please note these are all given to us in terms of pi. So if I want to know the area of this cross section, I need to first recognize that the cross section is a circle. So I'm going to use the area formula, pi r squared. So the radius of this circle looks like, the diagram right here is showing me that the diameter is 20, so the radius is going to be 10, and that's squared. So if I calculate that, and again, it's leaving it in terms of pi, that's going to be 100 pi. The 100 comes from the 10 squared, and I'm leaving my answer in terms of pi, so our answer would be C, 100 pi square inches. Next one, a right circular cone is 8 inches tall and the radius of its base is 9 inches. What is the best approximation for the perimeter of the planar cross section that passes through the apex of the cone and is perpendicular to the base? So many words there. So let's see if we can decode this and analyze it. So we're trying to find the perimeter of a shape. The perimeter of the cross section. So we've got to figure out what this cross section is, and then we can just add up the edges to come up with the perimeter. The cross section passes through the apex. So you need to know what the apex of a cone is, and an apex of a cone or pyramid is the tip top. So this cross section is happening right through the apex and it's perpendicular to the base. So the cross section essentially is going to be a triangle that is exactly this shape. I'm going to move that over so we can focus just on the triangularness of it. I know that this part of the triangle is 9, and so this also will be 9 for a total of 18. And the other information that I know is that the height right here is 8. That's not helping me. It's not part of the perimeter, but is an important part of the problem. So what we're going to have to do is calculate these diagonals, and this is a right angle, so we can use the Pythagorean theorem. So I'm going to call this x, and x for this triangle is the hypotenuse. So that is going to be the c in the a squared plus b squared equals c squared Pythagorean theorem. We're finding the hypotenuse. The legs that we know are 8 and 9 units long. So 8 squared plus 9 squared is equal to x squared. So if we calculate that, and don't forget, of course, to take the square root as you're calculating x, we calculate x to be 12.04. So as we add up the perimeter of that shape, and again, perimeter would be the distance around the edge of that shape, we have 12 plus 12 plus 18, which gives us 42. All right, one more. In the figure below, the shaded area is a planar cross-section that is perpendicular to the base of the right cylinder. What is the area in square centimeters of the cross-section? So we need to know what shape this cross-section is, and kind of has it in a shaded right here for us. So here's our cross-section. If we're imagining that in three-dimensional space, our cross-section is a rectangle. The cylinder itself is 40 centimeters tall, and that is going to be one of the edges of the rectangle, but we need to figure out what the other edge is. We need to figure out how long this is, which is the other side of the rectangle. So we're going to use this little triangle right here to help us. We have a radius of the circle right here, which is given to us as 15. And we know that this distance right here is 12. The distance between the cross section and the center is 12. And we can use that to figure out this distance. And it's key to note that this is a right angle, which means this is a right angle. So we've got this wee little right triangle in there. And all those colors are making me crazy, so I'm going to draw it again. So we've got one edge of our triangle here, one edge of our triangle here, and one edge here. And the right angle is between the blue and the green right there. So we know that the green edge of that triangle is 12. And we know that the red edge is the hypotenuse and it is 15. So we can use those two edges to calculate that other side of the triangle. In the Pythagorean theorem, this time 15 is our hypotenuse. So our equation looks something like this. So as we solve this one, we will have to use some subtraction. And we get x squared is equal to 81, which means that that side of the triangle is 9 long. Now maybe, hopefully my colors aren't confusing you now because the edge of this is not 9. So I'm going to switch that color to not blue because if we look at our cone up here, this edge is not just 9, it's actually twice 9. We have 2 of those, and they would be equal because this is another radius right here. So this edge is going to be 18 long. So our cross section is 40 by 18, which means that it will have an area of 720 square centimeters. And again, that's just 40 times 18. Okay, this is our last one. The figure below is a square pyramid. So when we say it's a square pyramid, that just means that the base is a square, which means that it is not a rectangle. It means this side is equal to this side. So which of the following is not a cross-section from this pyramid? Well, we can definitely get H. Definitely. Just by slicing parallel to the base. So that's not a problem. And we're trying to find the one that is not a possible cross-section. So that one definitely works. A triangle is also definitely possible if we slice down from the top, starting at the apex, we will get a triangular shape. So that one is also fine. So the other two are a little bit trickier to see, F and I. So I think that probably whichever one of these is correct is going to come from sort of angling our cut a little bit. So if I start cutting down from this spot about, and if I kind of just cut at an angle towards the base, I'm going to get a cross section like this. So because I'm cutting at an angle and because the pyramid is tapering towards the top, it's going to be narrower at the top than it is at the bottom when I slice at an angle. So this one is also just fine, which means the one that I can't get from a pyramid is the rectangle. Or I can't get it from a square pyramid at least. So, because no matter how, if I'm trying to get a rectangle, I will have to start angling a little bit, and as soon as I start angling, you have this exaggeration of the two sizes, so it ends up being a trapezoid. All right, so that's it for cross sections. Sometimes it's a little weird to get used to visualizing these, but you'll all be experts at it soon. So please just see your teacher if you're having any problems or need any help with that. Thank you.